Okay, let's jump right into this explainer. We're looking at the fascinating, highly technical sleight of hand required to really trick our human ears in virtual reality. Think about how far visual rendering has come lately, right? We've got photorealistic lighting, incredibly detailed textures, just these vast digital worlds that look absolutely convincing. But if you've ever put on a VR headset or played a really high-end game, you've probably noticed that the sound kind of lags behind that visual realism. It can feel a bit flat or just disconnected from the space you're looking at. You've experienced the magic of virtual sound, sure, but what you might not realize is just how incredibly difficult it is to make a digital room sound like a real one in real time. Today, we're unpacking some groundbreaking research on how to perfect this acoustic illusion and finally bring audio right up to par with the visuals.
So here's the ultimate puzzle for game developers and audio engineers. In the real world, when you clap your hands in a room, you aren't just hearing one single sound. You're unleashing millions of sound waves, and they bounce off the walls, the floor, the furniture, literally scattering in infinite directions before they eventually make it to your ears. Rendering all of those bouncing, scattering sound waves accurately on the fly, that requires immense, almost impossible computational power. So how do we get around this without literally melting your computer's processor while you're just trying to play a game?
Well, to solve this, scientists use a process called auralization. Auralization is essentially the mathematical art of building a believable acoustic illusion. It's about computing just enough of the sound's physical behavior so that your brain is completely convinced you're standing inside a cavernous cathedral with massive echoing halls, or maybe a cramped, muffled closet lined with winter coats, even if you're actually just sitting on the couch in your living room. The goal here is complete sensory deception.
Which brings us to part one, the anatomy of an echo. To successfully fake an echo, we first need to dissect the actual physics of it. To pull off this illusion, we have to look at the standard model researchers use, called the room impulse response. There are three very distinct phases here. First up, right at time 0, you've got the instant pop of direct sound. That's the sound traveling in a straight, uninterrupted line from the source directly to your ear. Second, arriving usually between 20 and 200 milliseconds later, are the early reflections. These are the sparse, distinct echoes bouncing off the nearest walls and surfaces. You can actually hear the geometry of the room in these early bounces. They literally tell your brain how big the space is. And finally, you have the late reverberation. This is the diffused tail. It's this chaotic wash of sound where thousands upon thousands of echoes overlap so densely that you can't distinguish them individually anymore. It just sounds like a smooth, decaying hum fading into silence.
And that leads us right into part 2, the mixing time dilemma. Because this right here is where the computational bottleneck happens.
Here's the catch. Simulating those first two stages, the direct sound and the precise early reflections, computers can actually handle that mathematically in real time. But calculating that chaotic late reverberation accurately? No way. That takes way too much computing power. It would bring a system to a complete grinding halt. So audio systems use an algorithm to totally fake that late reverberation. The million-dollar question for developers is, when exactly do you switch from the mathematically precise early echoes to the faked late reverb? This highly critical transition point is what's known in the field as the mixing time.
Because calculating that true mixing time on the fly is so intensely hard, currently developers kind of just guess. They might arbitrarily set the fake reverb to kick in somewhere between, say, 40 to 80 milliseconds. But there's a massive danger in guessing. If they bring in the fake reverb too early, it acts like a thick acoustic fog. It completely masks the real, precise spatial echoes. It destroys your ability to perceive distance and direction. You lose the entire sense of the room's shape, which completely shatters your immersion in the virtual space. Let's move on to part 3, simulating room acoustics. Let's see how researchers are fixing this.
To understand the fix, we need to look at the tools we actually use to simulate these virtual environments. You've got a stark contrast between two main methods here. On one side, ray tracing. It casts thousands of virtual sound rays into the digital room, mapping the whole space beautifully, including really complex physical phenomena like scattering. But because it has to calculate bounces infinitely, it is notoriously slow and super resource heavy. On the other side, the image source method. It is lightning fast, but it only calculates simple mirror-like reflections, and its computational cost absolutely explodes if you try to use it for those late complex echoes.
Let's look a bit closer at that incredibly fast image source method. The computer essentially plots these virtual mirror sources right outside the room's boundaries. It basically calculates a straight line from that virtual source to your ear to perfectly simulate how a sound bounces off a specific wall. Because we desperately need real-time performance to keep our games running smoothly, audio engines rely super heavily on this method for the early reflections. But like we established, it just can't handle the late reverb.
Now for the really clever part. Part 4. Measuring spatial incoherence.
So, since we're stuck using the fast image source method strictly for early reflections, researchers needed a breakthrough. How do you figure out exactly when to trigger the fake late reverb without the luxury of mapping the whole room with ray tracing? Well, here it is. Instead of needing a complete resource-heavy map, this new method analyzes the spatial data of just the early echoes. By looking at how these initial distinct sound waves interact with each other, the algorithm can actually predict the exact moment the room's sound field will become chaotic. It figures out the exact mixing time solely from those first few bounces. You can actually see this magic trick in action on these heat maps, which track how sound energy behaves in a room over time. Right after the sound happens, the energy is highly directional. You get these distinct sharp hits of sound bouncing around. But as time passes, you can literally see the sound energy spread out across the entire room. It shifts from clear directions to a totally smooth isotropic blur. The sound field is becoming perfectly diffuse. To actually measure that blur, researchers use something called the Comedy metric. It essentially measures the spatial incoherence of the sound. Without getting totally bogged down in the heavy math, it measures the eigenvalues of the sound field's covariance matrix. It's kind of like watching cream poured into coffee. This metric tracks exactly when the separate streams of cream merge into the dark coffee to become a single indistinguishable blur. Once the sound waves stop marching information and become totally mutually uncorrelated, the algorithm knows the sound is officially diffused. It found the mixing time. And amazingly, researchers found they can tightly predict this transition point using a streamlined formula based simply on the room's total surface area. Which brings us to our final section, Part 5, the future of immersion. Why does all this highly technical math regarding covariance matrices actually matter to you as a gamer or a VR user? Well, because it ensures that when a virtual monster creeps up behind you in a dark, cavernous digital room, the sound perfectly matches the physical properties of that specific space. By seamlessly stitching the mathematically perfect early echoes to the faked late reverb at the exact right millisecond, the system saves massive amounts of processing power. It completely avoids those nasty masking effects, meaning you can precisely locate the monster by sound alone, relying entirely on your natural instincts without ever breaking your immersion. The math behind real-time auralization is just evolving at an incredible pace. It's turning what used to be an impossible computational mountain into a totally seamless, real-time illusion that your brain fully accepts as reality. As we close out this explainer, I want to leave you to ponder just how deeply these acoustic illusions will soon shape our digital realities. Because if our machines can completely fool our ears into believing a digital room is entirely real, what other sensory illusions are right around the corner?